Hi, good morning.
Good morning, sir.
Yeah,
Good morning, sir.
good morning to all. Okay, in the previous class, we understood different optimization techniques, how to optimize the ARM assembly code. We initially understood preloading, okay, the data, required data for the next iteration and the previous iteration itself. So that is one optimization technique through which you can go for enhancing the performance of your program. And the other optimization technique that we looked into was loop unrolling. So by loop unrolling, again, you can go for avoiding the overhead branch instruction for the number of times you're unrolling the loop. And with that, we understood by doing the examples, so how the performance of the code after enhancing by using the loop unrolling technique improves when compared with uh, the performance of the original program. And this is what the performance is telling. That is, after improving the performance of after enhancing the code by uh, unrolling the loop. So we unrolled it for 4 times. So this is what the performance we are getting. So that means the performance of the program which is unrolled for 4 times is 1.57 times more faster than the original code. And initially we applied on the same code the preloading technique, and we got around 1.22 times more faster than the original code. So this is how the code has to be optimized for what giving the maximum performance. So these are all the things that we went through in the previous class. So now we'll continue our discussion on how to allocate the registers when writing the assembly code. Now, to understand this, because what we have is the limited registers. So if you take the microcontrollers, which are based on the ARM7 design, so they have 16 general purpose register. Again, in that 16 general purpose register, so 3 are reserved for the special use. Now, in case if your program is demanding for more number of registers than what are available, so then how do I deal with these things? So that is again one more optimization. Okay, so here basically you're going to learn how to deal with uh, the programs which are demanding for more number of registers than what are available. Okay, now in order to understand this, this is what the example which I'm considering. Say you uh, got into a situation where you got to shift an array of n bits, okay, upward in the memory by k bits. So assume you have an array of n bits stored inside the memory. So you can assume it as the data memory itself, because we have two memories. One is the core memory and the data memory. Assume you have an array of n bits of data, and you want this an array of n bits of data to be shifted upward in the memory by how many bits? K bits. Okay. So say for example, I have an array of say 5,000 bits stored inside the memory. Now I just want to shift all this entire array of 5,000 bits upward in the memory by 2 bits or 3 bits. So that is the k value. Okay. So even you can go for shifting it for 10 bits also. Okay. Now there is the next statement. What is saying? It is saying is, so we're assuming that n is very large and it is a multiple of 256. So the minimum number of bits that you got to assume that are stored inside the memory is 256 bits. Okay, and then what is the next value of n that you can have? Multiple of 256, 2 into 256, 3 into 256. It is something like this. So what we assume here is n is large. Why we say large? Because it is usually in terms of multiples of 256. And what about k? So what is the minimum number of bits that you can shift upward in the memory? Or what is the maximum number of bits that you can shift upward in the memory? So you can have the k varying between 0 to 32. That means the minimum number of bits that you can shift is 0. That means if you specify the k value as 0, so you don't have uh, an array of n bit shifted anywhere in the memory. It stays there in the same location. So maximum you can go up to 0 to 31. Okay, 0 to 31. 0 to 31 is nothing but 32 bits. The maximum number of shifts what you can do is 32 bit. So with this, this is what the problem statement we are considering in order to understand how efficiently the registers can be allocated if the program is demanding for the more number of registers than what are available. Now, before we go get into the details, how to shift this array of n bits which are stored in the memory or stored in the memory by k bits. So let us understand simple implementation of C function using which it is possible for you to shift the uh, array upward in the memory. Now here, see this, say for example, in is right now pointing to the array of n bits which are stored inside the memory. So that is what the in pointer is. And what is out pointer? Out pointer is what you need to compute. So you need to compute the new memory address where the data values will go and sit when you're shifting the n bit of array stored in the memory upward by k bits. So this is what you need to compute. Out is the value which you are going to compute, and n, as I said, it is the number of bits, an array of n bits stored inside the memory, and this n is usually the multiples of 256, and k is the number of bits to be shifted. Okay, so I have already written the tracing of this entire C function, so I'll show you. So don't consider this, so don't consider this also. So it was written over here. See, before I go there, let me tell you these two lines. So this is what the handwritten tracing of the C function which I've done. So the memory data, in the memory data, this is what the data I'm assuming. So I have the data. So this is one 32-bit data, and this is another 32-bit data. This is one more 32-bit data, and this is one more 32-bit data. And the addresses also I've written. The second row just below that is showing you the addresses. So this particular byte is at the address 00, and this particular byte is at the address 01. This is 02, 03, and this AA, okay, so is at the address 04. And my next 32-bit data is stored at the address 08. And my next 32-bit data CCC is stored at the address 0C, or the bottom one you can see here. So upper I've written it in hexadecimal, and the same thing in decimal below. And then DDD, so we have the upper one is 10, that is hexadecimal equivalent of 16, and this is the decimal address. So both have written. And you can just notice here, I've written in also. So in is the pointer which is pointing to this particular memory location right now. So hope people understood with this.
Yes, sir.
Okay, n is right now pointing to an array of n bit numbers which is stored in the memory. Now what you got to compute is the out. Okay, let me go back here. Okay, and carry, I'm initializing it to 0, and that is there inside the function. I'll show you. And k, I'm taking it as 2. That means, so my intention is to shift my array of n bits which are stored in the memory over here, starting from the address 04, and it is ending, say this is 16, so this is 17, this is 18, and this is 19. It is ending at 19 in decimal. So same thing if I go in hexadecimal, this is 1011, this is 12, and this is 13. The ending address is 13. So my uh, array of n bit now starting from the address 04, and it is ending at the address 13. Okay. Now, how do I shift this? So all these things I need to shift by upward in the memory by 2 bits, because I'm taking the k value as 2 bits. So don't look into these iterations right now. I'll explain. Now, just now, after all these iterations are done, okay, after the first iteration of, so after the first iteration of this do while loop is done, see it is written inside the do while. After the first iteration of the do while is done, so it gives me the address 16. So that means, so this data, my first 32-bit number, which is stored at the address 4, now goes and sits inside the address 16. Okay, it gets shifted upward in the memory. That means this AAA gets shifted upward in the memory, and now it comes and sits in this location. And similarly, so BBB, which was stored at the address 8, okay, earlier, now after the second iteration, so you can see the address computed is 32. That means it gets shifted upward in the memory by 2 bits. When I'm shifting it by 2 bit, it goes and sits inside the memory location 32. So this is what the newly computed. So these are the out values. In the first iteration, this is the out value. In the second iteration, this is the out value. In the third iteration again, see, C was stored at the address 0C, and once the third iteration of the loop is complete, do while loop is complete, it is saying this data is going to be shifted to the address 48. And where will this last data item DDD goes? It goes to the address 64. It is something like this. And this is the C implementation. Just for making you people understand what is that C implementation is, I've taken this uh, debugging in terms of the iteration. So what you're seeing here is for the tracing of the first iteration of the do while loop, and this is the tracing of the second iteration of the do while loop, third and fourth. So later, so what we do, we convert this C code into an equivalent assembly code, and then we go for understanding the allocation of the registers, and we also understand the difficulty what we are facing, because this demands the more number of registers than what are available. Then we go for looking into the solution for that. Okay, that is what we are trying to plan now. Okay, so now let us come here. See, carry is initialized to 0, and x is another local variable which is taken. Now what I'm doing now, you can notice here x is of type integer. Now x is equal to star in plus plus I'm doing. Now what gets assigned to x is the address of the first data element, that is 4. So let us come here. See, x, I have written here also, x is equal to start in plus plus. Now what is assigned to x is 04. The address is assigned. X is assigned with 04. Next, I'm computing the out. How I'm computing? See, out is equal to on x, I'm left shifting by how many times? 2 times. So what is the value of x right now? I'm writing here. What is the value of x right now? It is 04. How did you get the 04? Because in is pointing to 04. Sorry, going back. Sorry. Here. So in is pointing to 04. Okay. Now x is nothing but 04. Now on this 04, what is the operation I'm doing? So this is on 04, I'm left shifting. So this is left shift operator. How many bits I'm left shifting? So what is the value of k? K I'm assuming it as 2. K I'm assuming it as 2. K is equal to 2. Now this 4, let us write this in binary. So if I write this 4 in binary, 04 in binary, it is 0, 0, 0, 0, and then 0, 1, 0, 0. This is my 04. Now 2-bit left shift, 2-bit left shift on this gives you 0, 0, 1, 0, 0, 0, 0, 0. Okay. Now how much is this? So 2-bit left shift, sorry, not here. You get this one here. How much is this now?
16.
16. This is 16. Okay, this is 2 raised to 0, 2 raised to 1, 2 raised to 2, 2 raised to 3. This is 2 raised to 4. 2 raised to 4 is nothing but what? 16. And what is the carry? Now, this result of this operation is 16 now. 16, and you're doing bitwise ORing with the carry, and carry is initialized to 0. Now 16 or 0 is 16 itself. Here you do the bitwise ORing between the 16 and 0, we get 16 itself. That means the out value what I got now is 16. That means now the data value which is stored at the address, now the data value which is stored at address 04. So now this is the data value which is starting from the address 04. Now this entire data value will get shifted to the address 16 in the memory. And where is this address? Why we say it is upward? Because the memory addresses are increasing. Okay, so it gets shifted to the address 16. So this is what the 16 value that is computed, and the same thing is written over here. So 4 on 4, I'm left shifting it by 2 bits and then Ring with the 0, and this is what the value I get. Okay, and then I'm going for finding the carry. So carry will be 0. So always, as long as you're doing only 2-bit left shift or 3-bit left shift, the carry will be 0. So the moment you go for doing more number of left shifts, say for example more than 10 or more than 20 left shifts, then you'll get the carry. So in my case, I didn't get any carry. Okay, so now always when I do, so carry, how you're computing like this: carry is equal to x on x, you're right shifting. Right shifting how many times? 32 minus k. 32 minus k is nothing but what? 32 minus 2, that is 30. So if you go for right shifting 30 times on the x, what do you get? You get 0. X is now this 4. You right shift 30 times. Right, if you right shift 30 times, what will happen? see, first time right shifting, this 0 will go out of the register. Second time right shifting, this 0 will go out of the register. Third time right shifting, this 1 will go out of the register. And what gets added from the left end? All zeros. And what will be remaining inside the register? Everything is 0. OP people are able to understand.
Yes, sir.
Okay.
Yes, sir.
So now when are you going to get the carry? When this shifting amount is more. This shifting, now you're doing only shift 2 shift. Say in case I'm doing 30 shifts. Okay. So if I'm doing 30 minus 2 is how much? So 30 minus 2 is sorry, 30 minus 30 shifts I'm doing. 30 minus 32 minus 30. So you get 2. So now you got to perform only 2-bit right shift on this. If you're performing 2-bit right shift, this 1 comes to this position. So then you get the carry. As long as the shift amount is very less, you don't get any carry. So in our case also, we are not getting any carry. So we get the carry as 0. Okay, carry as 0. Now this is what the answer I'm getting, and this carry acts as input for the next iteration. Okay. It acts as the input for the next iteration. Now this 16 is the value I got in the first iteration. That means my first data element, first 32 number, gets shifted upward in the memory, and it gets located itself for the address 16. And similarly for the second one. Okay. So now say start in plus plus. It is a post increment operator. So now x is pointing to the next data address of the next data element, that is 8. So it is pointing here. So x value is 8. Now again on 8 I go for shifting to left by 2 bits. So how do you write 8? 0 8. 0 8 is nothing but 0 0 0. This is the binary equivalent for the 0, and for 8 it is 0. Oh, sorry. For 8 it is 1 0 0 0. Now 2-bit left shift on this. Now if we have this 1 coming here, and this is 0, and this is 0, so this becomes 0, this becomes 0, and this becomes 0. Now what is the value of this? This is 2 raised to 0, 2 raised to 1, 2 raised to 2, 2 raised to 3, 2 raised to 4, 2 raised to 5. 2 raised to 5 into 1. 2 raised to 5 is nothing but 32. So what you got is 32. Okay. So 32 is the value you got. And again finding the carry. So again you get it as 0. And then in the next iteration, so what you got is 48, and the next iteration what you got is 64. Now these are the addresses to which are my data element get shifted upward in the memory. So same thing we are doing here. After that, see from n, so n is very large I said, okay, from n. So after on every iteration, n I am decrementing it by 32 bits. Why? Because size of data is how many? 4 bytes. Say n is 256, so n value is 256. I have 256 bits to shift on every iteration. So I have a 4-byte data or a 32-bit data get shifted upward in the memory. Next, what I have to do? I have to go on keep decrementing this 256 by 32 bits. And the process I repeat as long as n is not 0. The moment n becomes 0, I stop the process and I come out. Hope people are able to understand this.
Yes, sir.
Okay, thank you. So, and don't refer this, these 2 slides. I'll be deleting these 2 slides. So because I've made a mistake here. The mistake is, so very simple mistake. And after that, I wrote this new one. Okay. Now what is the simple mistake I've done here? Say this is, yeah. So 1 is here. So I am performing 2-bit left shift on this. So after performing 2-bit left shift, so sorry, after performing 2-bit left shift on 4, this is what the data I got. Now, and this is what I need to OR with the carry 0. So, but here I have forgot to write this 1. I have taken it as 0 and I've solved it. So don't refer this. I'll be deleting after this session. Don't refer this also. And this is the correct one. Okay. Okay, fine. Now here. Okay, that's fine. So this is our C code is, okay, the function what we have written. Now I'm converting. So but looking into this C code, it is very difficult to understand how many registers are required, because this is a high level statement drawer of the high level code what we have written. So by looking into this, you cannot say how many total registers are required. So let us go for converting this into an equivalent assembly code. And this is what the equivalent assembly code you are seeing. Okay. Now before this, let me go to the next slide. All initialize. You cannot understand now what is this x underscore 0, y underscore 0, from where these things are coming. So let me come here. Okay. Now here I have, see, out is the variable name that is assigned to the register R0, and n is the variable name that is assigned to register R1. See how many registers I got to use. Just have a look into this. N is the variable name which I'm assigning it to the register R2, and K is the variable name which I'm assigning it to the register R3. So this out is the output register. Okay, so finally when the address is computed at the end of each iteration, it gets assigned to R0, and in is the what R1 is the register which holds the address of what the data items which are there in the memory, and N is holding the total number of bits, and that is R2 register. N is nothing but register R2. R2 is holding the total number of bits, and K R the register R3 is holding the number of shift amount. Okay, how much to shift upward in the memory. And next, see, I'm making x underscore 0 as an alternate name for the register R5, because these are all the things I require in my program. So, and x underscore 1 as the alternate name for R6, x underscore 2 as the alternate name for R7. So like this, where till where I've used till register R12, and see R0 to R4, R0 to R3 is used here, and R4, so I'm using here for y underscore 0. Okay, and again, so I have taken an alternate name, say y underscore 1, which is again pointing to the same register, which is that register R5 register. So there are two variables which are pointing to the same register. Now you can just look into the usage of the register. Now I have used R0 to R12, all 12 registers are used. Okay, but still I was not able to allocate register for this carry. So just look into this and tell me whether I have allocated register for the carry. So out I have allocated, in I have allocated, n I have allocated, k I have allocated for and I've allocated R5 to R12 for various other purposes, x0, x1, x2, something like this, and R4 is allocated for y0. Still I was not able to allocate the register for the carry, and still I was not able to allocate the register for kr. Now what is this kr? I'll tell you. So still I need two more register. Now I'm left with R13, R14, and R15, R15. Now, but these have the special purpose. So even though it says you can use R13, R14, R15 as general purpose register, but while using them, I got to be very careful. So before using this register, I got to take the backup of this register, and then I should be going for using. That means, so the registers which I was able to freely use as general purpose register, that is R0 to R12, are all utilized, and still there is a need for me to assign a register for carry and care. I don't have the registers. So I don't want to touch this. I don't want to disturb this R13, which is acting as stack pointer, R14, which is acting as link register, and R14, 15, which is acting as PC, program counter. So because they serve the special purpose. So I don't want to disturb them. So but from where can I get the register now? Okay, so now we'll come back. See this, look into this code right now. So what I'm doing now, since we go for using the registers, okay, so these registers R4 to R11, okay, so I'm just taking the backup. I'm storing everything into the save the registers. I'm saving everything onto the stack. So what kind of a stack it is? It is a full descending stack. All of you know what is a full descending stack is and how it operates, everything you know. And then in the next statement, so this kr I mentioned in the next slide, right? So this kr is this. So what I'm doing, a reverse subtract operation I'm doing. So from 32, I'm subtracting this k, and that value goes to kr, and that is what we were doing here. So 32 minus k we were doing, right? So this I'm doing there, okay? And I'm assigning that difference, 32 minus k difference, to the variable kr. So kr holds that difference, 32 minus k, and carry is initialized to 0. So but unfortunately, we don't have any register allocated to these two variables. Kr is right now not assigned with any register, and carry is also not assigned with any register. But I'm writing the program next year. So I'm loading the 8 words. Okay, so using the in pointer. Okay, so I'm loading the 8 words. 8 words I'm loading. That means 8 32-bit words I'm loading. So the first word I'm loading it into X0. What is X0 now? X0 is R5. Hope you people are able to understand.
Yes, sir.
Okay. So from my memory, using in as the base register, base address, I'm reading the first 32-bit number, I'm storing it into this X0, reading the second 32-bit number from my memory and storing it into X1. X1 is nothing but what? Register R6. Like that till R7, X7. What is X7? X7 is nothing but your register R12. So I've used all the register from R0 to R12. Come back here. Now I'm doing OR. Okay, so these two operations, what they'll do, so they'll perform the first iteration. Now I'm OR. Okay, I'm taking the carry. Okay, and taking X0, the value which is there in the register R5, and what is that I'm doing? You can just see here. So logical shift left by k bits. This is what the operation I'm doing now. This what operation? This operation I'm doing. Okay, and after doing this operation, what you got to do? You got to R that with carry. So one single instruction we are doing it. See, logical shift left, because the second operand can be pre-processed using the barrel shifter, which is connected to one input of the ALU. So we just try to recall the data flow architecture of the ARM core. Okay, so shift left, shift a logical shift left by k bit, and or that with carry, and the result goes to what? Y0. What is Y0? Y0 is the same register. Y0 is your R4, sorry. Y0 is your R4 register. And now in Y0, okay, you have the first iteration address. So where the first 32-bit data should go and sit inside the memory, upward in the memory. And similarly, what I'm doing next, see, in the next statement move, okay, I'm finding the carry, new carry. And then this is for the second iteration. So this is for the third iteration. This is this two. R and move is for the fourth iteration. This R and move is for the fifth iteration, sixth, seventh, eighth. Now, can you just tell me what I'm doing over here? Loop unrolling. Loop unrolling. So in this code, I've also done loop unrolling. How many times I've unrolled it? How many times I've unrolled it?
8.
8 times I've unrolled. That means on every unrolling, I've avoided this BNE. So because this BNE, so what it was doing, it was consuming 3 additional clock cycle, one for computing. So 3 additional in the sense, one is useful clock cycle, that is it uses it for computing the address, but the other 2 clock cycles, so they were the flush clock cycles. They were used in order to flush the pipeline and let the target instruction get into the pipeline. All these things we have understood in the earlier classes. So now what I'm doing, so this BNE is avoided for 8 times. That means you're able to save 8 into 2. That is equal to 16. 16 clock cycles you're able to save. Is this not an optimization? Yes or no?
Yes, sir.
It is an optimization. So because you're avoiding those two flush cycles which were required for BNA on every unrolling. So here 2 cycles you saved, here you saved 2 cycles, here you saved 2 clock cycles, here you saved 2 clock cycle. Like this, 8 into 2, 16 clock cycles you're able to save. Okay, so one kind of optimization is there, but the other kind of difficulty is that, so we are not able to yet allocate the register for carry and what the KR variable. So that's it, fine. Okay, now we'll continue to the next. Okay, so okay, this is fine. One thing is fine. Okay, we have unrolled it for 8 times and we were able to save 16 clock cycle. But the major problem is what? So improving the efficiency of the loop by unrolling. Unrolled it for 8 times. Okay, it's good, fine. But still, the possible ways to deal when we run out of the register, and that is what we are facing in this. We have run out of the registers. So one thing is I have to go for using R13, R14, R15. No, I don't want to disturb those registers because they serve for the special purpose. R13 is acting as stack pointer, and so even stack pointer is also used here in this, if you notice. So SP is also used. SP is also used. I cannot touch that. And SP is also used. And I cannot go for using the link register. I don't want to disturb the program counter. Now, how to deal with these things? So here is the solution I'm showing you. Reduce the number of registers required by performing fewer operations in each loop. So this is one thing. So simple technique. Now what we have done here, say I have unrolled it for how many times? 8 times. 8 times I've unrolled. So I have the lack of registers now. Now why you want to go for unrolling it for 8 times? Unroll it for 4 times. Unroll it for 4 times. So if you're unrolling it for 4 times, in each iteration, you're able to load how many words? 4 words. So that is what it is saying. In the previous example, we could load 4 words in each load multiple rather than 8. So that is what we did. We loaded 8, x0 to x7. 8 words we loaded. So why you want to load 8 words? Load only 4 words. So if I follow this, so then obviously I get the registers. So hope it is clear.
Yes, sir.
Okay. Now if I'm loading only 4 words, what happens? So I don't have to use from what see R5, R6, R7, R till here it is sufficient. And what about these registers? They become available. Hope you people are able to understand. Still, I get 4 registers. Okay, that is one thing what it is saying. Okay, so use go for loading 4 words in each load multiple rather than 8. So this is one thing. Other thing what you can do. Oh, no. I want to do 8 times unrolling. I want to load at a time 8 words. Then what you have to do is you have to go for using this stack. You have to completely depend on the stack instead of depending on the registers. Okay, now an alternate code implementation to free up more register. Okay, so next this solution we consider in the next example. So that is what we are considering here. Now what we do, so the modified implementation, one is go for reducing the number of unrolling. Another one is no sir, I don't want to reduce the number of times I'm unrolling, so I want to unroll it for 8 times itself. Then go for using the stack. No, sir. I don't want to use the stack also. I don't want to reduce the what unrolling number also. Unrolling number must be 8 itself. And then I don't want to use the stack. Then what you can do, you have another solution. What is that solution? Go for modifying your implementation. Code implementation you modify. And this is what the solution we are going to discuss now. See what happens if I reduce from uh, uh, 8 unrolling to 4 unrolling. Again what will happen? See, 8 unrolling, 8 number of times unrolling to 4 if I reduce, so how many clock cycles I'll be able to save? 4 into 2, that is 8, only 8. Still there is 8 clock cycles wasted. Okay, no, I don't want to waste even those 8 clock cycles. I don't want to use the stack also. Why I don't prefer using the stack? Because performing the operations using the register is much faster, because my intention is only to optimize the code. So if I, so okay, 8 times I want to unroll, I don't want to use the register, I want to completely depend on the stack. Where is the stack? Stack is there in the memory. Every time you have to go and get the data from the memory, and that itself consumes more number of clock cycles. I don't want to go with the stacks, and even I don't want to sacrifice with the number of times I'm unrolling now. I want to do 8 times unrolling itself. So what does that have to do? I can go for modifying my implementation. So this is where your creativity comes into picture. Okay, so just look into this program. So what else I can do for making my program in this case itself work as it is and provide 100% efficiency. Okay, so what is that we do now? So this is, see, if we look into this program, so the carry value need not stay inside the same register. So I need not reserve what explicit register for storing the carry. Why? So because we notice that the carry value need not stay in the same register. We can start off with the carry value in y0, and then move it to y1 when x0 is no longer required. So if you do this, see, you start the carry well with y0. As in when you're proceeding with the iteration, say first unrolling is done, and when you go to the next unrolling, you pass the value which is there in y0 to y1. You need not reserve an explicit what register for holding the carry. So simply the carry can be forwarded using the same available registers from one. So this is y underscore 0, sorry, and this is y underscore 1. So it can be simply forwarded from one register to the next register without having to explicitly allocate a register for holding the carry. Okay, and then okay, so we solved the problem with the carry. Now how do I solve the problem with the kr? Because I need one more register for storing the kr, right? So okay, you can go for using lr, because we are in this. I'm not calling any subroutine. Am I calling any subroutine? See, lr is required only when you're calling the subroutine, because the return address gets saved onto the LR link register. Since I'm not calling any subroutine in my code, so that means LR will not be used. Okay, now LR can be used. This is what the modification we are doing, and the modified code is here. Okay, so you can just observe now. See, so I'm again, how many words? I'm not sacrificed. I'm not gone for 4. I'm loading the 8 words itself. And earlier I used to write a separate carry. No, I don't have the carry now. Okay, so now we have, so first initially it is an y0, and then it gets transferred to y1, and then it gets transferred to y2. So like this it goes. OP people are able to understand?
Yes, sir.
And what is the register for kr? So I'm making use of the link register. It's a sequence here, kr, r, and lr. Because since I'm not making a call to the subroutine here, say LR will not be used. I know for sure LR is not being used because I'm not calling any subroutine. Let us go for using LR for storing our kr. So done. My job is done. Say I got the solution for the register problem, and even my program executes with the same performance. Okay. So this is what. So this is the kind of optimization that we look in. And all this thing where we were able to do, in the assembly code. That is what you have to observe. So initially I started with the high level code. See, now here if you just look into this, any number of times if you scratch your head, it is not possible for you to identify how many registers are required. Okay, you cannot do that. And it is also not possible for you to say how many times I can go for unrolling this. So all these things, okay, optimizations what I did in the lower assembly level code cannot be done here. You cannot do that here. Now when I write the assembly code, see all this optimization techniques what I mentioned now, they are directly in my control. I can go for uh, putting all these optimizations to my program, and I can enhance the performance. That is the reason we say always the assembly codes run very much faster than any of the language or the program which you're writing in the high level language. So they get executed much faster. See, if you're looking at the performance of the program, then it is always better to write the program using the assembly code, because you get the direct control of the optimization tools. Okay. That's okay. So modified implementation, I told you. Okay. Okay. So I modified it. Okay, good. So I was able to, how many registers we were using here? We have used LR as well. Okay. Up to 14 registers, I can go for modifying my implementation. I can apply my creative skills and I can work out. Okay, even after applying the creative skills and all these things, say my program is demanding more than 14 registers. Then what I have to do? Nothing I can do. So it is behind my limitation. So then the only solution is to depend on the stack. That's all. So you push everything onto the stack, and whenever the data is required, go for popping them in the reverse order. So this is the only solution. And next. Okay, we have something called as map and field assembler directives. So we haven't used these two assembler directives in our program. And are we going to use these two assembler directives in future, sir? No, we are not going to use them. So, but it says, so it is possible for you to define and allocate the space for the variables and array on the processor stack. How? So like this. Say map 0, I'm saying this is an assembler directive. What it says? It says the starting address as 0. So even if you don't want to start it from 0, you can give any address. And then I have a variable A. Okay. So and field 4, I'm saying. What this will do? It says A is a variable of, so A is a 4-byte integer variable, which is starting from the address 0. Next, I need another variable B. Okay. But I don't want this variable B to hold a 4-byte data like something like this. I want it to hold only 2-byte data. Okay. Now what I'm saying, so what this is going to do, it's going to it makes B as a variable of 2-byte integer, at an offset 4. Why at an offset 4? Because from 0 to 3, we have A occupying, because this is 4 bytes. So if I'm writing here something like this, the memory array, so A is starting from 0 and it'll go till 3. And the next we have B starting from 3 and it goes, sorry, let me take it as 1 to 4. So starting address I'm taking it as 1 to 4, and B is starting from the offset 4 and it will go till where? Since it is only 2 bytes, 6. And next I'm declaring one more. C field 2. Now what I'm saying, C is again an integer of 2 bytes. Now it is starting from the offset 6 and it will go till 8. C and then 8. And next D field 64. 64 bytes in need. Okay, so we have this D starting from now offset of 8 and it will go till 64. That is 8 plus 64 is how much? So that is 52. Hope people are able to understand.
Yes, sir.
See, if you don't want to use stack, say what stack does it it also says you can push 8 bytes of 4 bytes of data. It keeps consuming 4 bytes of memory. If you have the variable, if you need to allocate the memory for the variables which are of varying sizes, so then this is what you can do. See, we have only 4 bytes allocated for A, and 2 bytes allocated for B, 2 bytes allocated for C, and 64 bytes allocated for D. So this is what can be followed. Okay, so this is another thing what the ARM assembler provides. So it provides two directives called as map and field. So using map, you can specify from where the memory allocation should start for the list of variables which are about to define. And using the field, you can define how much of memory should be allocated to each of the variable. I guess you understood it.
Yes, sir.
Okay. So next is, so making most of the available registers. Okay. See, I have a register, and all of you know in ARM7, the capacity of each register is 32 bits. Capacity of each register is 32 bit. Say R0 to R15 registers we have, and the capacity of each register is 32 bit. So all the time when we're writing the program, we don't go for making use of 32-bit data. So sometimes say I want to store the value 5 in my register, only 5. Do you need 32 bits to represent this 5? So tell me how many bits are required for representing this 5? How many minimum bits are required for representing this 5? Do I need 32 bits?
No, sir.
No. How many bits are sufficient? 101. This is 5, right?
Yes, sir.
This is 5. How many bits? 3 bits are sufficient. 3 bits are sufficient. So I want to represent 7. How many bits are required? Again 3 bits. 1, 1, 1 is nothing but 3. Sorry, 7. So I want to represent 15. Now what is the minimum number of bits required for representing 15? Can I go for representing 15 in 3 bits? Can 15 be represented using 3 bits?
No.
No, it is not possible. Now what is the minimum number of bits required for you to represent 15? 4 bits. 1, 1, 1, 1. Okay. So this is 2 raised to 0, 2 raised to 1, 2 raised to 2, 2 raised to 3. Hope people are able to understand.
Yes, sir.
So this is 8 plus 4, that is 12, plus 2, that is 14, and plus 1, 15. So similarly, so I want to represent 16. What is the minimum number of bits required? Can I go for representing? Is it possible for me to represent the 16 using 4 bits? Not at all possible. I need 5 bits. 1, 0, 0, 0, 0. This is what is my 16 in binary. 16 in binary. Okay. So now, say if I want to store, say for example, say if this is a 32-bit register, and to store 15, I require only 4 bits, something like this. Now I say I want to store, say number 12, number 13, number 15, number 14. Okay. So to store this, I need 4 bits. To store this, I need 4 bits. To store this, I need 4 bits. And to store this, I need 4 bits. Now, what is the total number of bits required? 4 into 4.
16.
16 bits I need. Okay. Now, how many such numbers it is possible for me to store here in this 32-bit? So I can go for storing 8 such values, 8 such data values. So just imagine one register holding 8 different values. Okay. So whenever I'm assigning some data to my register, so even if I'm assigning an 8-bit data at 16-bit data, what is happening? It gets sign extended to 32-bit. Hope people are able to follow.
Yes, sir.
Somewhere, if I can manage this, when I'm assigning some data here, so I don't want it to get sign extended and occupy the entire register. Say I want to assign 5 to this register. So 5, I know it can be represented only by using 3 bits. Now, but still, when I'm storing this 5 into the register, what happens? It gets extended and it is made as, so this 3-bit number gets converted into a 32-bit number. Now, how it get converted into 32-bit number? All the bits from towards the left of this one, they get 0. How many zeros will be there? 28 zeros here. So 28 zeros, and then it gets stored over here. And we know that these zeros doesn't have any meaning. Hope people are able to follow.
Yes, sir.
Now I got to make use of some trick where and that trick, what it should do, it should allow me to store multiple values in one single 32-bit register. It should allow me to store multiple values. See, now you can imagine, so one register, you are storing 2 data or 3 data or 4 data. Say if you want to store 3-bit numbers, 3-bit numbers, so how many such data you can store inside the 32-bit register? You can go for storing 8 data. Imagine 8 data in one single register. Is that not an optimization? Yes, it is an optimization because it reduces. See, there are several tricks you can use to fit several sub 32-bit length variable into a 32-bit register, and thus you can go for reducing the code length and also increase the performance. So how it increases the performance? The code length, obviously it reduces because one single register you're storing so many data. Say 3-bit number, something like this, 8 numbers I'm able to store, the code length obviously reduces. And you can ask me, sir, storing 8 data in one register, how can it increase the performance? Yes, it improves the performance. You read one register. Reading one register will give you how many data? 8 data. Imagine that itself is the performance. You just read one register. How many data you're accessing? You're able to access 8 data. So assume each of this data is stored in 8 different registers. How many reads are required? You got to read 8 registers. Okay. To get There's 8 different data. So that is now what are those several tricks? So what is the time? 10:54. I don't think so. This needs some time because I got to explain. See here in this, it's a 32-bit register. I'm storing 2 different datas. So this is increment as one of my one data and index is my another data. Now next, so we got to trick and see how to access only index from this. So that is again, see I'm storing multiple things. So but when I need only index, how do I access in only index from the register? When I need only increment, how do I access increment data from the register, same register? So that is a trick, a small trick. And again, when I say trick, it is not a very big trick and complicated trick. Very simple trick it is. So whenever I want to access this data, I need to perform the write shift by 16 bits. Whenever I want to access this data, I need to go for masking these higher 16 bits. So this is the only simple trick. Okay. So whenever I want to access this index, now what I do, I perform 16-bit write shift and get this index to this position. Sir, this 16-bit write shift we have to do in order to access this. Is this not again the what additional operation we got to do in order to access the data from, and is it not going to consume additional number of clock cycle? Remember, what we are doing here is the logical operations, and the logical operations are the much fastest operations than compared to any other operations. Okay, so logical operations are always much faster. So logical ending, logical Ring, logical NOTing, and logical shifting operations are also much faster. OP people are able to understand. I guess I think let me stop here. From here we'll continue in the next class because this requires some time. So now it is already almost 10. Okay, still I need to take attendance. I don't want to disturb the next class. Let us stop here. Any doubts?
No, sir.
Okay.